Back on section 4.4. A little late on the record button. First thing I do is identify the vertical asymptote. The vertical asymptote is a value of x that makes the bottom of the expression equal to 0, but not the top. If it makes both of them 0, remember that that makes a hole in the graph. In order for it to be a vertical asymptote, the limits have to become infinite, either going to plus infinity, minus infinity, or one of each. Something is a horizontal asymptote if that's the value of the expression in the long term. The ends of the graph form the horizontal asymptote. So we look at really big negative numbers and really big positive numbers, what they do to the fraction. The fraction is controlled by its degree. If the degree on the bottom is bigger than the degree on top, then the x-axis is the vertical horizontal asymptote. If the degree on top and bottom are the same, then you just look at the ratio of the coefficients. If the degree on top is bigger, if we have a top-heavy fraction, then the ends of the graph will just go to infinity, and there is no horizontal asymptote. So in our example, the bottom was equal to 0 when x squared minus 9 is 0, and that's at plus and minus 3. This has the same degree on top as on the bottom. And so using that thing right here, the ratio of the coefficients, 4/1, becomes the limit. Then to get the rest of the graph, if we just do as usual, take the derivative and then analyze the sign with the quotient rule, our derivative simplified to this. Our critical numbers occur when the numerator is 0, and that only is when x is 0. And now we're fixing to check the sign of f prime. We do have to include the two asymptotes because they can make this thing change its sign possibly. So we're looking at the sign of f prime. Let me do it right here. So I got to move the camera a bit. I'm going to put 0 in the middle and then plus and minus 3 on each side. That's an asymptote, so I'm going to show it off like that. And 0 is a place where the derivative is 0. So I'm plugging things into here. And now use your advantage that the denominator is squared, so I don't really have to plug anything in there. When I square it, it's positive. So all I gotta do is take my test point, multiply it by -72, and that'll give me the sign of f prime. So if I put a -4, multiply -4 by -72, my derivative will be positive. If I take a -1 and multiply it by 72, my derivative is positive. But if I take any of the positive numbers from this interval or that interval and multiply them by -72, we'll get a negative number. So on the left side of the asymptote, the graph rises. In between the asymptote, the graph rises and falls. And then on the right side of the asymptote, the graph drops. That gives us a relative maximum at our critical number. And there is no relative min. Let's put all the finer details in the graph right here. Let's put our 3 asymptotes in there. There's x is -3. There's x is +3. And then we need to stick in y is equal to 4. So I'm not going to keep the scale right. Let's just put y is equal to 4 right here. We'll plot our critical number. When x is 0, so is y. F of 0 is 0. So in here, we've got something that has a relative max. So it's going to come up and come down. to the left of the vertical asymptote, my graph is either going to be up here and stay up here, or be down here and stay down here. And this will tell us what it does. I've got to have a graph that leans like this. So there's no way I could put it in here, because then it's going to cross my asymptote. It's going to be up here, and it's going to be concave upward, kind of like that. So it goes to plus infinity on the left side of -3. It goes back to y is equal to 4 as x goes to minus infinity. Then on the other asymptote, the graph has to lean down this way. So again, it's going to have to be above the horizontal asymptote in order to do that. Right? I can't put it here, and it won't approach the asymptote. I got to put it up here because it has to lean in that way. So it's going to be concave upward there. Okay. So that's kind of a comprehensive view of what we did last time. Did you get a chance to try any of these in your busy lives? Rub this off and we'll continue on with what we were doing last time. What I wanted to do is show you an example of a function that has two horizontal asymptotes. Most of them have just one. Here's the function has two horizontal asymptotes. Because it has a different limit as x goes to plus infinity than it does as x goes to minus infinity. Let's look at the limit as x goes to plus infinity. And the function is 2x divided by the square root of x squared plus 4. That limit is going to be different than the limit as x goes to minus infinity. Other than me telling you they have different limits, what makes you think that they're going to have limits at all? What's the highest power in numerator and the denominator? X to the 1. This down here in the denominator also behaves like an x to the 1. So the degree on top acts just like the degree on the bottom. Now here's the difference. If I take a big number, the first thing I do down here is I square it. So if it's a big positive number, it stays positive. If it's a big negative number, it becomes positive. So here, the denominator has a coefficient of the highest power of x, always a positive 1. If I take a big number that's positive and put it in here, it stays positive. But now take a big negative number and put it in here, and it becomes negative. So they act with the same degree. They both grow as an x to the first power, but this grows as a positive 2, and this grows as a negative 2. You see that? This up here is going to be negative, but this down here is going to be positive. This up here is going to be positive, and this down here is going to be positive. So they grow at the same rate, but one's growing like a positive 2, and the other one's growing like a negative 2. So this one's going to +2, and this one's going to -2. There are no vertical asymptotes because x squared plus 4 is never 0. I try to find them by setting the denominator equal to 0, I get a sentence that says x squared is -4. Ha, I laugh at that. X squared can never be negative. So there are no vertical asymptotes. So what we know is one end goes to +infinity, one end goes to -infinity. Anybody interested in what's happening in between? Maybe, maybe not. Do you want to take a derivative of this and look at the first derivative? Got a bunch of boardroom, may as well. Let's see what the graph of this looks like by analyzing the sign of the derivative. So suppose you want to graph f of x. It's 2x, and let me put that as a power. I'm going to graph that maybe. Let's move it over. This is going to be bad recording, isn't it? What we decided over here was that when x is a positive big number, this behaves like a positive big number. This behaves like a positive big number, both acting as a first degree. So that got us to x is 2. But if x is a big negative number, this behaves like a negative big number over the positive big number. So the ratio of the coefficients gives us then a negative. All right, now we're going to take the derivative and check the sign of this thing. So we're doing the quotient rule. We've got the bottom times the derivative of the top, x squared plus 4 to the 1/2 times 2, minus the top times the derivative of the bottom. So I bring the power down, raise that to 1 power less, multiply by the derivative of what's inside. And then all of that over the bottom squared. And the bottom squared just gets rid of the 1/2 power. I'll do that in the next step. Here I'm going to simplify this primarily by simplifying that second term in the numerator. I'm going to put all these terms together, and I'm going to write that with a positive power. So here I'm going to have 2 times x squared plus 4 to the 1/2. Here the half and the 2 gives us 1, but then that with that gives me a minus 2x squared. That's going to be underneath. And then I said when I square the radical, I lose the radical.
Why 2x squared and not 4x?
Because remember, see that half in the middle? That's going to cut that 4 down into a 2. Now I'm going to quickly clear the fractions from my numerator by multiplying the entire top and the entire bottom by x squared plus 4 to the 1/2. That'll clear the fraction when I distribute that through there. And so let's distribute it. That times that one, we add the exponents and we get rid of the radical. So I have 2 times x squared plus 4. That times that one cancels, so it just leaves me minus 2x squared. When I multiply these two, I add exponents. So I got a first power and a half power. The end result is x squared plus 4 to the 3/2 power. And then if we kind of do 2 steps in one here, I'm going to get a 2x squared from here, but minus that 2x squared is going to give me 0. So all I'm going to have left on the top is a positive 8. There are no x's in the numerator, which means f prime is never 0. The denominator is never 0 because I've got an x squared plus 4. So there are no critical numbers. What on earth is that going to happen? Let me check my arithmetic again. I think everything's okay. Okay, let me see. Notice that no matter what value of x you put in here, you get a positive number. The 8's the positive, x squared plus 4 is positive, x squared plus 4 to any power will be positive. So I've got a function that's always increasing. There are no relative max or mins because I didn't have any critical numbers. So it's going to have to change concavity, but I don't want to look for that because that second derivative could be pretty messy. So let's put our 2 horizontal asymptotes in here. We said one of them is going to go to x is equal to 2. That's the one on the plus infinity side. X is equal to 2. Y is equal to 2. That's what I want to say. The right end of the graph approaches this line. The left end of the graph, as x gets to be minus infinity, goes to this line. In between, I've got a function that is always increasing. So it's going to have to go through here. It does indeed go through the origin because it's got a 2x on top. So we've got to make it come through here and tail ends approach those 2 lines. Increasing, but approach those lines. So it's going to look a lot like an x cubed graph. We've got this asymptote over here and that one over there. No max, no mins, always increasing. Okay? So it's more boring than you wanted it to be. But this is an example of when you could possibly have 2 horizontal asymptotes. You'd have to have some sort of action like a square root of an even power. And then that same power on top. Okay, you've got one of those hiding in your web work. Not hiding because I just pointed it out. Okay, one more bit here in this section. And that's graphing things that have what we call cusps or sharp corners. I've graphed some with the asymptotes already, so maybe I'm going to skip that. And I'm going to go, maybe I'll do the second one. Let's do one more with asymptotes. Put it right here. The function f of x is equal to x squared minus x minus 2 divided by x minus 3. Our goal in this problem is to graph it, identify relative max and mins, but also identify asymptotes. So I'm going to ask you to fill in these blanks. Let's see what we can do with just the first derivative. Right off the bat, though, the first 2 planks, the asymptotes you can get just by looking at the degrees and looking at the expressions that we have in the numerator and the denominator. In this particular example, the degree on top is bigger than the degree on the bottom. What does that say about the horizontal asymptote? There are no horizontal asymptotes. The top grows faster. No horizontal asymptotes because it's top heavy. That means the ends of the graph will either both go up or both go down. They're going to infinity or to minus infinity. They're not going to a horizontal line. Vertical asymptote comes from where the bottom is 0, but not the top. Find any place where the bottom is 0? X is equal to 3. X is equal to 3 does not make the top 0 because 3 squared is 9, minus 3 is 6, minus 2 is 4. So the top is not 0. So X is equal to 3 is the only vertical asymptote. Now I want to see if you can take the derivative of that and simplify it enough to find any critical numbers. So try a quotient rule and see if you can find any critical numbers. I'm curious to see if it does simplify. I'm gonna start my derivative over here and you guys keep going. Good to that part, right? Quotient rule. Now we got to FOIL that out. Keep going. 2x squared minus x minus 6x plus 3. One's not going to change anything, so minus x squared plus x plus 2. So I'm going to have a 1x squared. That's gone with that. So minus 6x plus 5. Good to there? Do you have any factors of 5, both with the same sign that add to a -6? 5 and 1, so I can factor that as x minus 5, x minus 1. So that means that f prime is going to be 0 twice. When x minus 5 is 0, and when x minus 1 is 0. So 5 and 1 are both critical numbers. Was anybody able to get that far before I interrupted you so rudely? Now, when we check the sign of the derivative, make sure you include the vertical asymptote in your sign chart. So I've got 1, 5, and then 3. So x is 1, x is 3, x is 5. That's a normal break. That's an asymptote. That's a normal break. We can put the sign of f prime. I've got 4 intervals I need to check out. But I only really need to worry about what the sign of the numerator is, because look again, the denominator is squared. Whatever I stick in for x, after I square it, the sign on bottom will be positive. So I'm going to put my test points into the numerator. Here I'll use x is 0. So if I put x as 0 in both of those, both factors are negative. But when I multiply the two negatives together, that becomes positive. If I put x is equal to 2 in there, the first factor is positive, the second factor is negative. Positive times negative makes that negative. When x is 4, I have a positive times a negative. So that's still negative. And when x is 6, both of them are positive. So the graph is going to go up, down, down, up. So it increases to the left of 1, from minus infinity to positive 1, and then again to the right of 5. It decreases between 1 and 5, but it does neither at 3. Remember, 3 is an asymptote. So I'm going to say it decreases from 1 to 3, and then again from 3 to 5. Do any of our critical numbers give us a relative maximum? X is equal to 1. And then it turns around the other way around, x is 5, so that's the minimum. Now let's see if that's enough to tell us what the graph of this thing looks like. Let's put our asymptote in here at 3. Okay. No horizontal asymptote. Let's plot our two critical numbers. Let's find f of 5 and f of 1. F of 5 gives me 25 minus 5 minus 2 over 5 minus 2. So let's see, 20 minus 2 is 18 divided by 3. F of 5 is 6.
-3.
Oh, that is a -3. So that's a 2. So when I say I got on top, I got 18 divided by 2 is 9. Now let's plug in x is equal to 1. F of 1 is 1 minus 1 minus 2 over 1 minus 3. So a -2 over a -2 gives me a +1. So let's put 1, 2, 3, 4, 5, 9 right here. And 1, 1 right here. Over here, we have to rise until we hit 1 and then drop. And so we're going to rise until we hit 1. I need my red. Come up, hit that, and then drop. Here we're going to drop and then rise. So remember the asymptote in the middle, that's what's going to curl this graph down like that, and kind of hug here and go up like that. Would you like a fun fact?
Yes.
This function has yet another type of asymptote called a slant asymptote.
That is very funny.
Isn't it? A slant asymptote occurs where in functions with a degree on top is bigger than the degree on the bottom. If you imagine a line coming through here, this end is going to hug that line. This end is going to eventually hug that line. We can find the equation of that line by going back to here and using long division. When the degree on top is bigger than the degree on the bottom, you're going to get a whole part plus a remainder over the divisor. The whole part is going to be, in this case, a first degree equation. And that's going to be the equation of the line that is the slant asymptote. So let me remind you how to do long division. Slant asymptote occurs when the degree on top is strictly bigger than the degree on the bottom. If the degree on top is just 1 bigger than the degree on the bottom, then you'll have a line as your slant asymptote. If the degree on top is higher by more than 1, then you'll get some sort of other graph. If I divide the bottom into the top, I look at how many times this divisor goes into the lead term. And it looks like I need to multiply it by x to get it there. So my first term in my quotient is x. Now, if I multiply both of those by x, I get an x squared here and a minus 3x there. Then in long division, you always subtract. Subtract that line from the line above it, and the x squareds are gone. A minus x minus a negative 3x gives me a minus x plus 3x for a positive 2x. And then when I look again, this x goes into 2x 2 times. So I put a plus 2 here, and then I get a 2x minus 6 here. And when I subtract, I get a positive 3. This is our slant asymptote. So it goes through 0, 2, and then it has a slope of 1. And then this end of the graph is technically going to do something more like that than what I've drawn. Still has the maximum there, but it's going to now bend toward that line. Same thing up there. Do anything like that when you took pre-calculus in high school? Long time ago in a previous life, or 2 years ago for most of you?
I haven't even heard of long division until I got in this class.
Yeah?
Yeah.
Wow. I used to love that as a kid. I still kind of love it because I'm a weirdo.
Were you teaching him?
Okay, so the other example that I had on graphing functions with asymptotes, I think we did a version of that. Let's go down and look at graphing functions that have cusps or vertical tangent lines. So cusp is another name for a sharp corner. But it's also going to be a place where there's no derivative. The function is going to be defined at that point, But you'll find that when you take the derivative, it's a place that makes the denominator of your derivative 0. So it's where f prime does not exist, but f does. There's a y value there. And it's going to be a place there about which the concavity changes, either that way or tip it upside down. We can have a vertical tangent line. Again, f prime does not exist, but f does. Here's my does not exist. But a vertical tangent line is where the graph itself becomes steep. So there might be a change in concavity. Here, there's no change in concavity. There is. And the tangent line here just becomes vertical just for a brief instant. This type of thing usually happens not when you have a rational function, but a function that has rational exponents. So let's look at my next two examples here. Whole number exponents keep things bending in ways that we expect, kind of like polynomials. But rational exponents do some of those weirdo things. So my first example looks like f of x is equal to x minus 3x to the 1/3. Some Monday morning markers here. I need something that writes a little bit better. See if I put anything in here. Wait, that is a marker. It's green. It needs green. Don't have any. Just have to make these bad boys work.
I have some uncolored ones if you want.
Fun colored. Let me see if this will guy work. It says it's dry erase. Let's see. Okay, so notice that this thing has a cube root. We can take the cube root of any number in the world, positive, negative, 0. So this is a function whose domain is the set of all real x's. But once we take the derivative of it to get the critical numbers, let's do all the stuff that we did before. Make you a blank for the critical numbers, increasing, decreasing, inflection, relative max, relative min, inflection point, concave up, concave down. Let's go through our whole graphing process. Dark enough to show up. So we're looking for the usual suspects here. We'll get them by taking the derivatives. Let's go take the first derivative of that. Do it over here a bit. The f prime looks like 1 minus, now I'm going to bring the power down. The 1/3 is going to multiply with the 3 to give me a 1. 1 power less, 1/3 minus 1 is a negative 2/3. That negative sign on that x puts it in the bottom. So I have 1 minus 1 over x to the 2/3. So now that it's on the bottom, automatically the value of x that makes that 0 becomes a critical number. And the only number to a power that gives us 0 is 0. So this tells us right now that x is equal to 0 is a critical number. And it's where f prime does not exist. Dividing by 0, major no-no in all of mathematics. But now we're going to get some other critical numbers, perhaps, if I set that equal to 0. So now let's set f prime equal to 0, and we're solving this equation. We'll do that by taking the negative term to the other side, and then we'll multiply through by the denominator. And then multiply both sides by x to the 2/3, so that goes up here. So I got to do two things. I've got a cube root squared. I'm going to get rid of the cube root first by raising both sides to the 3rd power. That leaves me an x squared on the left and a 1 on the right. The next step is to get rid of the x squared by taking square roots, plural. When we take square roots, we get two critical numbers, x is plus and minus 1. So a grand total of 3 critical numbers. X is 0, and x is plus and minus 1. Now let's put that on a number line and work on getting the sign of f prime. So here's x is -1, x is 0, x is 1, and we want the sign of f prime. I'm going to have to take a number and take its cube root. So let's try to pick a number in each interval that we know the cube root of. Like back here, let's use -8. The cube root of -8 is -2. Then I square it and I get a +4. So I have 1 minus 1/4. That's positive. In here, I'm going to use -1/8 as my test point. Put -1/8 in here and take the cube root and I get a -1/2. Square -1/2 and I get a +1/4. But now I have 1/1/4. How big is 1/1/4? So that becomes 4. 1 minus 4 is negative. Let's take +1/8 in here. Cube root of +1/8 does the same thing, gives me a 1/2. Square is 1/4. Flip it becomes a 4. So that's a negative. And over here, if I use a +8, cube root of 8 is 2, 2 squared is 4, 1 minus 1/4 is positive. So my graph is going to rise, fall, fall, rise. So it increases to the left of -1. And then again to the right of 1. It decreases from -1 to 0. It does neither at 0. Remember, at 0, I've got no derivative. And then it decreases between 0 and 1. And the location of the relative max. X is -1. And the relative min? All good with everybody? Okay, so let's next look at the sign of the second derivative. The second derivative, the derivative of 1 is 0. Now I'm going to bring this -2/3 down. That makes that a +2/3. Take 1 away from that, and I get a -5/3. And so I get 2 over 3x to the 5/3. So f double prime does not exist at x is 0 as well. Once f prime doesn't exist at x is 0, all of the derivatives beyond that won't. Let's check the sign of f double prime by plugging numbers in around 0. Let's take a -1. Cube root of -1 is still -1. -1 to the 5th is still -1. Times 3 into 2 gives me negative. At +1, everything stays positive, right? So I got a graph that's concave down and then concave up. So I got the inflection point, x is 0 because it changed concavity. Concave up to the right of that. Concave down in between. And now the big finale, we get the graph. Let's go back to the original function and plug in all 3 of our critical numbers. F of 0 looks like 0 to me. F of 1 is 1 minus 3 is a -2. F at -1 is -1. Cube root of -1 is -1. Times this 3 now is going to make that a plus. So that's a +2. All right. Move the camera a bit. That way. We'll put all that stuff over here. We've got the 3 points of interest, -1, 2. 0, 0. +1, -2. We have a relative max here. We have a relative min here. We got the vertical tangent line here. Right, that's what we meant by no derivative. Then we've got to make the graph go up, down, and up. But sharpen it right here so that the graph is nearly vertical. That will make the vertical tangent line. Back here, it's going to be concave down. To the right of 0, it's concave up. So instead of making it just like a 3rd degree graph, make it stand up pretty sharp right here. Come down like that. And then turn around like that. But the graph becomes vertical right around that point. And we knew that because of the change in concavity, but not the change in the direction. Here we'll have the opposite. We'll have a change in direction, but not the change in concavity. So let's look at another example that does the sharp corner. And I think that'll be the next one. The next one looks like 2x to the 5/3 plus 5x to the 2/3. Two x to the 5/3 plus 5x to the 2/3. We're going to do all this stuff again. So I'm going to erase my results from the last problem. You've got all that written down already. While I erase, you guys take the first derivative and see if you can find critical numbers. In particular, find the critical number that's going to make the derivative not exist. I think this one still has 3 critical numbers. Let's see if you can get all 3 of them. that second term, it's going to have that negative power. And that puts that x underneath that one term. Again, x of 0 is going to be the place where there's no derivative. But you got to be able to simplify this well enough to find the other critical numbers. And then multiply the 5/3 with the 2, I get 10/3. And when I take one away, 3/3 from 5/3 leaves me 2/3. Back here, I get another 10/3. Take one away from that, and I get a negative 1/3. So let's take that x to the negative 1/3 and put it on the bottom of that second term. I'll just put it down there with the 3. Then when you're taking derivatives and end up with an x on the bottom, take a stop and identify the x on the bottom as giving you a critical number. So x to the 1/3 is 0 when x is 0. X is equal to 0 is a critical number because f prime at 0 does not exist, f of 0 does. Now we'll set that equal to 0 and try to solve for x the way we did before. Split them across the equal sign, cross multiply, and see what good things happen. That one over here. Only one critical number. You tell me. Cross multiply that 10 by the 3, multiply the negative 10 by 3, multiply 10x to the 2/3 by 3x to the 1/3, cross multiply. This times this gives me negative 30. This times this will give me a positive 30. X to what power? X to the 1, add exponents. So I get negative 30 is equal to 30x, divide by 30, and I get negative 1 is equal to x. That's my other critical number. So my critical numbers are x is equal to 0 and x is equal to negative 1. And let's remind ourselves that at x is equal to 0, we have no derivatives. So a little mark there, make sure we remember that. Now we're going to look at the sign of the derivative. So let's go back to here. And we're going to plug numbers again for x to see if that's positive or negative. And our two numbers of interest are negative 1 and 0. Again, a third power is a cube root. So let's pick a number we can take a cube root of. Back here, we use negative 8 again. The cube root of negative 8 is a negative 2. Negative 2 squared is 4. So that gives me 40 over 3. Plus, now I'm doing it over here. Put a negative 8 here. Cube root of negative 8 is a negative 2 times 3 gives me a minus 6. The actual number doesn't matter. Can you tell me whether that number is a positive or negative number? Positive, right? This is 80 over 6 minus 10 over 6. Now in here, let's use a negative 1/8. Maybe I need to do this on the board instead of in my head. Cube root of 1/8 is a half. So I have a negative 1/2 squared. And then here I just have a negative 1/2, a cube root. Cube root. So that's a fourth. That becomes 10/4. 10/4 divided by 3 is 10/12. And this becomes 10 divided by a negative 3/2, which is a negative 20/3. 10/12 is 5/6. 5/6 minus 20/3 is 5/6 minus 46. It's going to be negative. And now here, let's just use x as 1. I've got 1 to any power is 1. So I have 10/3 plus 10/3. That's positive. So our graph drops, drops, that's a plus sign, rises, drops, rises. So I got it increasing to the left of -1, and then again to the right of 0. And I've got it decreasing between -1 and 0, giving us a relative max at x is -1, a relative min at x is 0. Leave all that. All right, let's whip out another derivative. I'm taking the derivative from here. So that f double prime is going to equal to 20/9 x to the -1/3 minus 10/9 x to the -4/3. We write that with positive exponents. Let's get my calculating out of the way here. This becomes 20/9 x to the 1/3 minus 10/9 x to the 4/3. I'm going to set that equal to 0 with the observation that the x on the bottom again gives us x is 0 as an inflection point. Now let's split our fractions up, cross multiply, and see what happens. Let's take this one to the other side. So I cross multiply, and this gives me 90x to the 1/3. Over here I get 180 x to the 4/3. Doesn't clean up as nice as that other one did, but if I move this back to the other side, I'll be able to factor. Those guys have a common factor of 90x to the 1/3. If I take 90 out of 180, I get a 2. Take x to the 1/3 out of here by subtracting exponents, and I get x to the 3/3. So I get a 2x, and then minus 1 here. So this confirms the inflection point at x is 0, but I have another one when 2x minus 1 is 0 at x is 1/2. So my inflection points are 0 and 1/2. Now let's get the sign of this. Let's go back over here. Let's put a -1 here and a -1 there. -1 to the 1/3 is a negative. So that's a -20/9. -1 to the 4th power is a +1. So that's a -10/9. -20/9 minus 10/9 is negative. If I put a +1 in here, well, here now, I have 20 over 9 minus 10 over 9. So that's a positive. In between these two, let's use our 1/8. So 20 divided by 9, 1/8 to the 1/3, minus 10 divided by 9, 1/8 to the 4/3. So I get 20 over, that's a half, 20 over 9 halves. And that's 10 times 9. Half to the 4th is 1/16. We flip and multiply, so I get 40 over 9. Flip that, I get 160 over 9. So that looks like it's a negative number. So I have concave down, concave down, concave up. Now for the big finish, we plot our 2 points. So let's write this down first. Concave up to the right of the half. Concave down to the left of 0. And then between 0 and a half. The 2 points I want to plot are these. F of 0, 0 to any power 0. F of -1. -1 to an odd power is a -1, so that's a -2. -1 to an even power is a +1, so that's a +5. I got the ordered pair -1, 3. I think the graph will fit right here. We got 0, 0. We got -1, 3. I have a graph that goes down, up, down, down, up, down. It has no derivative here, and it has a horizontal tangent line there. It's concave down back here to the left of 0. Between 0 and a half, it's concave up. And then, I'm sorry, between 0 and a half, let's scoot that over here so that's right here. And then the rest of it is concave down. So that tells me that, let's see, I want it concave down, I just wrote it wrong. Pay attention to what I'm saying and not what I'm doing. Wait a minute, I just said it wrong the other way. Concave down, concave down, concave up. Is that what you're pointing out?
Well, I think you put the point on the wrong side of the y-axis.
Oh, I think you're right. That hurts. Let's fix that. My hero. I got -1. -1, what was the y value? Where did I put those? -1, 3. 0, 0. Horizontal tangent here. Vertical tangent there. I've got up, down, up. I got a half about right here. And I got that it is concave down here. Between 0 and a half, it is still concave down. And then from half on out, it is concave up. The concave down part is going to give me this around that no derivative point. We got follow the green dotted line, something like that. Stay concave down, but follow the green dotted line puts me to here. And then just the little jiggle makes it concave up. Pretty cool little graph, huh? You don't want your typical boring polynomials. So be aware when you have a denominator that gives you 0. It's either a sharp corner or one of these guys. Sometimes the second derivative will help us out. Sometimes it'll give us some deep doo-doo. This was not easy to analyze the sign. I kind of went through that kind of fast. But be on your toes. Just look out for things like that. All right. I didn't get to answer any homework questions. So I'm willing to stick around after class. Do you have any individual questions? And we'll start section 4.5 next time.